Section 7.8 it's titled The Relationship Between Active, Reactive, and Apparent Power. So what we're going to do is we're going to see how the three defined powers are interrelated. And for the first time, we've gone through this chapter and we're through 9 sections. We're into the 9th section and we've not got one new equation. So we're also going to introduce some equations for us to work through and put some numbers to this and quantify some things. And hopefully this is starting to make a little sense. And there's some really good visuals that we look at with this as well. Okay, so let's dig into this one. Looking at figure 711, we've got a lot of meters, right? We look at this to begin with. Here's our source, and here's an amp meter, and this amp meter is measuring all of the current. And then here is a voltmeter here. And of course, that voltmeter is connected such that it can read all the power, all the voltage that the load is seeing here. And then the wattmeter would be connected such to measure the voltage and the current so that we would be able to indicate the active power. And then here's a var meter that is developed so that it can measure the reactive power. And of course, out here is our load. All right. So there's a lot of stuff that we can do in relation to this. And so let's go through and say, what is each thing measuring to begin with? So the voltmeter is measuring voltage. The amp meter is measuring current. And the wattmeter is measuring power in watts. And the var meter is measuring reactive power in positive qvars, okay, or vars. So knowing that both the active power and the reactive power are positive, we know that the load itself absorbs active power and absorbs reactive power. So what that tells us is, it's this type of load that we looked at earlier, right, or in the section before. So that's what it tells us. And then, so if that's the case, there is an resistive component and there's an inductive component to this. But if we looked at the overall composition of this, we would know that the line current, because there's no capacitive part of this, right? It's inductive and resistive. So the line current is actually going to lag the voltage by a certain angle. All right. And then so as we look down below here, as we look down at this, we can see that the active current is in phase with the voltage, as we would think. The reactive current is 90 degrees lagging of the voltage since it is inductive. And so what we're trying to determine is the sum of the two currents. Now, like I said before, this is the first time that we have been able to offer some equations to help us work through some things. But, again, from this setup that we have right here, and if we were in the lab, this is something that we would do. But we know that the for the the active current, well, let me write this first. The power in watts is equal to I sub P times E. Solve for active current, that would be power divided by voltage, and that's just equation 7.1. We can do the same thing over here for Q, and Q would be I sub Q times E, same voltage source. Solve for I sub Q, that would be Q divided by E. All right, so you got to get used to using these new designations. Not everything is power in watts anymore. All right, so once we know that, we can also determine that the apparent power, which is really the sum of the two types of power, and it is S. So S is equal to E times I, and if I'm trying to solve for this current here, that is going to be S divided by E, and that becomes equation 7.3. Okay, so far so good. Does that make sense? Now, if that were the case, and that's what I'm working with, then if I wanted to determine what the total current is here, then I could solve that looking, we're looking for this quantity here, so we're using just, basic Pythagorean or right angle, whatever you want to call it, you know the drill, but I squared is equal to I sub P squared plus I sub Q squared. All right, then solve, well, let's just leave that alone. Excuse me. Let's just leave that alone for a second. Now, we defined I here as this, S divided by E. So why don't I do this? I'm going to take S over E, since that equals I from here, right? And I'm going to put that in its place, and I'm going to do this. I'm going to do the same thing over here. I sub P of I sub P is power over, or P over E squared. And then here again, here is I sub Q, and we said that that was equal to Q over E, and we got to square that. And that becomes something that we can minimize, or we can solve this, right? We can take this common, we can get rid of this common factor, this E, we can factor it out of there, and we end up with this very important equation 7.4, which says that S squared is equal to P squared plus Q squared, right? And this is a wonderful equation, lets us do a lot of different problems. The apparent power squared is equal to the active power squared plus the reactive power squared. And of course, that can be solved, just depending on what we wanted. If we wanted to determine what that is, we'd take the square of both sides. We could do all this different calculations as we go through that. But let's wait and see what he wants us to do. And he also says we can calculate the value of this angle. We can calculate the value of this angle here in the phasor diagram, because the tangent of the angle is equal to I sub Q over I sub P. Okay, I sub Q over I sub P, right? The tangent of the angle, opposite over adjacent. So if I wanted to know what that value was, he says arc tangent, but I think we're more used to inverse tangent designation. But again, he writes this as arc tangent of I sub Q over I sub P, right? But really what we're saying, and then again, if that's the case, right? If that's the case, then I have this relationship here that I can also express arc tangent of Q over P, and that will give us the value of that angle. Now, I don't know about you guys, but when I look at this, I used to write this as, excuse me. that, and you know, I don't even know if, and you guys have been in a math class since me, you know, we say inverse tangent, but you know, so instead of saying arc tangent. But anyway, this defines equation 7.5. Now, these are all real good and all very useful, but I don't think we're going to see that until we work a problem. So let's try something here. And the first simple power problem that we'll do will be example 7-4. And then let's see, gosh, okay, then we'll make another video for 7.5 and 7.6. But he says in 7.4 that I have an AC motor and it absorbs 40 kilowatts of active power and 30 kVAR of reactive power. Okay, so you know that's the situation that we've been looking at here, right? And so the it's you know, active load, reactive load, and so he says calculate the apparent power of the motor. Now we've got all these neat equations. The first one, or one of the most useful ones, is this 7.4. So we're going to use that. He says, what is the apparent power of this? And I was starting to do this the last time. So I will rewrite that as this. Now I'll actually take it to the step that I do this. Okay. And so this becomes this value. And now I have 40 squared plus 30 squared. And we, we've been around that long enough. The classic 5 and 4 that we do when we're learning that relationship. But anyway, if this is 40 kilowatts and this is 30 kVAR, excuse me, then this is going to be 50 kVA for apparent power. And again, this is the sum, the vector sum of the reactive and active power. All right, let me stop there. And then we've got a couple more neat little problems we'll work, 7.5 and 7.6.